So in the previous introduction to separated sets, we defined what it means for two sets to be separated. Now we are going to see some applications of that concept. We defined this in the previous session. We have defined that. So now what are we saying? We are saying that two disjoint closed sets in a topological space are separated. How can we prove that? Two disjoint. Actually, it sounds obvious. Two disjoint closed sets. They are disjoint, so automatically they have to be separated. So how can we see this technically? Two disjoint closed sets are separated. So Roman 1. So we are going to let A and B be disjoint closed sets in a topological space. Let A and B be disjoint closed sets in a topological space X. So this implies that since A and B are closed, so the closure of A is equal to A, closure of B is equal to B. Since A and B are closed sets. Now we want to show that those two sets, A and B, they are actually separated. So A and B disjoint, so they are also disjoint. Also A intersection B is an empty set. So if you want to show that they are separated, then we show that they satisfy this definition. So then A intersection B closure is actually equal to A intersection B closure, which is B, and this is an empty set. Also A closure intersection B is equal to A closure is A intersection B. This is an empty set. So this implies that A intersection B closure is equal to A closure intersection B, and this is equal to an empty set. So this implies that A and B are separated. Full stop. Now we have to look at part 2, the proof of 2. What does 2 state? 2 is saying that two disjoint open sets are separated. Two disjoint open sets are separated. So we are going to let A and B be disjoint open sets in a topological space X. Since they are disjoint, then A intersection B is an empty set. So what do we want to show? We show that for A and B to be separated, we show that A closure intersection B is equal to A intersection B closure, which is an empty set. We are supposed to prove that. We prove that. The proof is going to follow contradiction. We are going to first contradict those two statements. So by way of contradiction, suppose by contradiction that A intersection B closure is non-empty. Suppose by contradiction that set is not empty. So this implies that since it's not empty, there exists an element X in A intersection B closure, and this implies that X is in A and that X is in B closure. So this implies that X is in A and and X is in the closure of B. Now you have to evoke what it means for a set to be in the closure, for a point to be in the closure of a set. What does it mean for a point to be in the closure of a set? So if X is in the closure of B, by definition, that implies that every neighborhood or open set, every neighborhood or open set containing X intersects with B. That is the definition of a point to be in the closure of a set. A point is in the closure of a set if every neighborhood containing that point meets with B. Every neighborhood n of X meets with B, as in this intersection here shouldn't be an empty set. Then a point will be in the closure of that set. So every neighborhood or open set containing X intersects with B. So observe that A is a neighborhood of X. A is a neighborhood of X, i.e. A is an open set, containing, i.e. A is an open set containing X. Hence, is an open set containing X. Hence, by this assumption, every neighborhood or open set containing X intersects with B. So A is an open set containing X. Hence, A intersects with B, implying that A intersection B is not an empty set. Observe that this is a contradiction. It's contradicting what? It's contradicting the fact that A and B are disjoint. It's contradicting the fact that A intersection B is empty. So this implies that, and the contradicting the fact that A and B are disjoint, implying that our original assumption was actually wrong. So this implies that A intersection B closure is an empty set. Similarly, we can also prove following the same argument. We have that A closure intersection B is an empty set. You can also prove this. You can start by contradiction. Suppose that the set is not empty via the same thing. It's just a matter of changing the roles of, because here we had B closure. So to prove this, you just change the role of B. Now B, what was B closure means is interchanged to B, and originally what was A now becomes A closure. You just interchange the roles, then you realize that this is also an empty set. So we have it that in a topological space X, disjoint closed sets are actually separated, and disjoint open sets are actually separated.